Next experiment is Thevenin's and Norton's theorem. We will combinedly see the experiment in a single video. So Thevenin's theorem. Thevenin's theorem states that in any linear bilateral network consisting of more number of sources and more number of elements can be successfully simplified into an equivalent circuit which is having a voltage source in series with the R equivalent of the individual elements. So that is Thevenin's theorem. So for Thevenin's theorem, we will take example circuit as same circuit what we have taken earlier in superposition theorem, 2.2 kilo ohm, 3.3 kilo ohm, 4.7 kilo ohm. So these are the main circuit. So here we will keep an ammeter and with a load in series 1 kilo ohm. So this will be the main circuit. Thevenin's theorem states that in any linear bilateral network comprising of more number of sources and more number of elements can be successfully replaced with a single element in series with a voltage source. Instead, using n number of elements, we can replace with a single element, and the voltage applied here is equals to open circuit voltage measured. This voltage can be called as V Thevenin's also, V Thevenin's voltage with R Thevenin's. So we have to prove this Thevenin's theorem that the response of this circuit is equals to the response of this circuit. Then Thevenin's theorem is justified. Instead of using this circuit, we can successfully replace this circuit with the equivalent circuit. Complexity is reduced. To make complex networks into simple networks, we will make use of Thevenin's theorem. So for that, in 3 cases we will prove the theorem. In case 1, what we need, this voltage we have to know to convert this circuit. First we will see the response of this circuit, IL. So the current of this individual element circuit. Case 1. So take the current by connecting an ammeter here with a series load. This will give you the I1. Okay. So put the value of I1 here. Case 2. So we should know voltage. This is a reference, checking reference to justify the theorem. Now let us come to the actual circuit. This is called open circuit voltage, which will be measured by removing the load resistor and keeping a voltmeter in replacement of load resistor. 2.2 kilo ohms, 3.3 kilo ohms, 4.7 kilo ohms, and connect a voltmeter across these two terminals and measure the V Thevenin's voltage which is required to set the voltage in the equivalent circuit. And what else we need? R Thevenin's we should know. To take the practical value of R Thevenin's, we have to replace the voltage source with a short circuit. Everyone knows this, and keep all the resistors as it is by making use of multimeter or VI method also you can do. So we will see multimeter uses, that is R Thevenin's. So making use of this multimeter, we can measure the resistance value by keeping all the elements as it is. So this multimeter you have to set in ohms mode, and the common terminal is common always, and put the red terminal in the voltage ohms measurement knob. By using these two terminals connected across these elements, we can take the value of resistance value. So I will show you practically later. So this is the method we will find out the R Thevenin's. Next checking is response of this circuit, equivalent circuit. This is case 3, and case 4, final checkup. So it should equals to the response measured here. So final checkup, we will set the V Thevenin's voltage which is measured here, and we will take the resistance value which is equals to R Thevenin's here, take an ammeter in series with a load resistor and measure this IL dash. When IL equals to IL dash, theorem is proved. The response of the individual element circuit is equals to the response of the single element circuit. Then the theorem is proved. In that way we will prove the theorem. So first we will take case 1. See this case 1 circuit. All the elements are arranged as it is, 2.2, 3.3, 4.7. Right? So voltage I have taken and connected to the voltage positive is connected to the R1 end, and here I need an ammeter. So I'll take ammeter positive terminal which is connected to the 3.3 R2 end. 3.3 ending is connected to ammeter, and a load resistor 1K. So I will take a load resistor which is having color code of brown, black, black, brown. So this is 1 kilo ohm. So ammeter negative terminal is connected to load, or otherwise at the end also you can take, here also you can take the current, but so we will make difference between this junction and this junction. We will keep load resistor like this. So here we will place nearby the ground terminal, because load resistor second end is connected to ground. So ground terminal we will take in this junction. Now it is task for us to place the ammeter. See that terminals are properly connected in the same vertical line where we are connecting here. So this is same in vertical line. We will keep another first terminal of the load resistor somewhere else like this to make the connections for ammeter, and ground is placed in this section, and ammeter negative is connected to positive taken here, positive terminal is taken here, and negative is connected to 1K second first end. This makes the connection. Set the voltage. Let us consider, I have not given the voltage, so we can take any reference voltage. So let us take 10 volts. See the connections. Current response of this current is 1.2, you can see. So I'll put the value of IL is 1.2 milliamps. First we have taken the response of this circuit, right? So case 1, it is over 1.2 milliamps. Let us come to case 2. Remove the load resistor, ammeter, and replace with a voltmeter. So I'll remove the load resistor. This load resistor is removed. Remove the ammeter and take the voltmeter. This is voltmeter. Connect voltmeter across load end and measure VOC, open circuit voltage, in the same section. How much it is? 6.77. This is 6.77 volts. Right? Now remove the voltage source in this section. Case 3, R Thevenins. We should short circuit these two ends. So voltage source is removed. Switch off the circuit, and this is also not required. And take a connecting wire and short circuit R1 end with the ground. So short circuiting R1 with ground like this. Right. Take the multimeter, put it in ohms mode. These two terminals leads to make contact with at this ends. So multimeter is showing the resultant R equivalent as 4.73. In that way we will measure the resistance value 4.73. Now we can successfully connect. We know the value of V Thevenins, we know the value of R Thevenins, and response is to be taken in series with load. So I will replace all the resistors and I will keep only one resistor, which is 4.7, which is R Thevenins. So I will keep this R Thevenins here. Remember, the input voltage which is given in the equivalent circuit is equals to the open circuit voltage measured open circuit voltage what we measured 6.77. You need to set that voltage 6.77. So voltage positive is connected here as shown in circuit diagram, and ammeter. So we have to take ammeter and connected to the R Thevenin's end, and we'll make a gap between R Thevenin's end and positive terminals of ammeter and negative. Negative I have placed here, and now I'll take the load resistor which is to be connected in the circuit. So there is load here 1K. So I'll make contact with 1 kilo ohm. So I'll make contact it with ammeter negative, and source negative is taken to load resistor. So what is the voltage we need to set? Input voltage should be equals to 6.77, not 10 volts. So make sure of that. Everyone do the same mistake by setting 10 volts and verify the response. It won't match 6.7. See, so it is actually 6.77. So what is the current? 1. Which is equals to this response 1.18, something like that, 1.1. So both are matching, so we can successfully replace the complex network into the simple network by making use of Thevenin's theorem. That's all.